again, vintage electronics. John, tell us what we're going to look at today.
Well, this morning I thought we'd take a look first of all at a tube tester, because if you're working on tube radios, it stands to reason you're going to have to test tubes at some point. So I wanted to talk about a couple of different types of tube testers that were out there and show you an actual demonstration of how a tube tester works and how to test a tube. There were basically three different types of tube testers made during the history of radio, let's say, from the very beginning. In the 1950s, there was a type of tube tester made. It was a very inexpensive tube tester, mostly for hobby use or technician use if they were in the field maybe. And basically what it did, it was just a filament supply voltage with a neon bulb in it, and it tested whether most of them had 4 common sockets on it, 9-pin, 7-pin, a loctile and an octal socket, and it would test basically whether the filament had continuity or not. If you had no continuity, of course the tube's bad to start with some general exceptions that I'll talk about in a second. The next step up was what's called an emission type tube checker. What an emission checker did was to put out a DC voltage. You plug the tube into the tester, and a DC voltage was applied to the plate, and filament voltage was applied to the filament. There was a meter in the plate circuit that would determine if the electrons were being boiled off of the cathode and caught by the plate. Now we're going to have, in the demonstration here, we're going to have a diagram that comes up that shows you the operation of a vacuum tube. And what basically happens, if the vacuum tube has a filament in it, just like a light bulb, it glows and heats up and heats the element above it, which is called filament in it, just like a light bulb. It glows and heats up and heats the element above it, which is called around it, which is called the cathode. The cathode is a material that's very rich in electrons, usually something like copper or some other metals, sometimes exotic metals that are very rich in electrons. As the filament heats the cathode, the free electrons boil off of the cathode, and a positive voltage is applied between the cathode and the plate. The cathode's negative, the plate is positive with a high voltage generally, or relatively high voltage, and those free electrons are attracted to the plate, being that they're negative and the plate's positively charged. So you have a stream of electrons flowing through the tube to between the cathode and the plate. The way the tube actually operates is that they insert an element, and this is a very simple explanation of it, but they insert an element between the cathode and the plate called a grid. And what the grid is basically doing, it acts as a valve or a regulator. A signal is applied to the grid, and it begins, as the signal is applied, it begins to trap the electrons that are going between the cathode and the plate. And as the signal varies, it varies the amount of electrons that are allowed to continue to flow. Just like if you were controlling a water faucet, turning it fast and slow. And so what is applied to the grid as a low voltage or a low signal level is then amplified by the tube, because the plate is at a much higher potential in the grid, so the output waveform coming off the plate is then the same configuration as what's on the grid, but at a much higher level, and that's how the tube amplifies.
The British actually call it a valve.
They call them valves. That's true. Now there are exceptions to this rule. There were tubes that were made called cold cathode tubes. One example was an OZ3 rectifier tube, or OZ4, I think. There was 2 of them that were used in early car radios. They had no filaments in these tubes. They were what they called cold cathode tubes, and they were used as rectifiers in a lot of the early car radios that had tubes in them. So there are exceptions to the rule, but basically that's how a vacuum tube works. Now the third type of tube checker that was a very expensive and top of the line kind of issue, and you found them in a lot of high-end service shops like RCA and places like that, was called a mutual transconductance tester. What the mutual transconductance tester did that the emission checker didn't was that it actually put the tube into a working circuit, and it checked the gain and what's called mutual transconductance, or G sub M, the actual ability of the tube to amplify or regulate a signal. And so if you want to test the tube, the most effective or the most accurate way to test it would be a mutual transconductance tube tester. In today's market, the mutual transconductance tube testers that are still around are prohibitively expensive. I mean, unless you have $400 or $500 to invest in a tube checker. That's what you're going to pay for a mutual transconductance tester that's working out on eBay. You can still find plenty of tube testers on eBay. The emission type checker, like the one we have several of them here at the museum, but I have this one here that's made by Superior Instruments. It was a very common tube tester back in the 1930s and 40s, and it does what we need it to do. So we keep this particular model not only as a display for the museum, but also as part of the equipment here in our restoration shop. I'm going to give you a demonstration of how the tube tester, how to go about testing a tube. But one thing that I wanted to point out is that if you can't find a tube tester, you can build a emission type tube checker relatively easily. One of the restrictions or restricting issues that they had back before solid state was that the transformer in this tester had to have a tap on it. It was basically an isolation transformer, 110 volts in, 110 volts out. But the secondary side of the transformer had taps on it for every voltage that the tube tester could test. So in other words, you had taps for 1.5 volts, 1.8 volts, 2.5 volts, 4 point something volts, 5 point something volts, 6 point something volts, 12 volts, all the way up to the 35Z5, 50L6, and 117 L7 M7s, which were tubes that actually, where the filament actually operated directly off a line current at 117 volts. Today, with solid state regulators, you could basically do the same thing by having just a plain isolation transformer, 110 in, 110 out. You have to produce a 110 volt DC supply, which you do just simply with a diode or a rectifier. You need a meter, because the meter is going to have to be there to tell you what the electron flow is. And of course, you're going to need a set of switches and things, or jumper cords that you can use. A lot of people are building tube testers right now with jumpers instead of switches, because it's hard to find these old rotary switches with so many multiple settings on them. But you can do it with jumpers. And basically, what you do is you use a regulator, a solid state regulator for the filament, with a number of resistors to control the different voltages that you want to use for your filaments. And then that's really all there is to it. Once you get the filament up to the right voltage, you apply plate voltage to the plate and measure the electron flow with a meter in the plate circuit, to a milliammeter or whatever. It would probably be a milliammeter in most cases in the plate circuit. And that's all you need really to check and see that the tube, A, that the filament's lighting, and B, that the tube still has free electrons available on the cathode, that the cathode has not deteriorated to the point where there's no more electrons to boil off of it, which is what happens when a tube gets weak. And so you can test the tube generally. You have to estimate your own settings, or figure out your own settings once you build it, as to what's a good tube and what's a bad tube and what's a weak tube. But it can be done if you can't find a tube checker. If you want a tube checker, go out on eBay. There's plenty of them. If you have to restore them, basically most of them are nothing but a simple power supply with a rectifier and a filter capacitor, plus this transformer. So as long as you get one with a good filament transformer, it's worth paying $100, $125 for one if you have to. And it's an essential instrument for checking tubes. Now, you can check a tube in a radio with an ohm meter across the filament, and that'll tell you if the filament's good generally, but there's no way that test can tell you if the tube's capable of actually working as a valve, as a tube.
And of course, you can always just use your eyeball and see if the filament's lighting.
Well, this is true too, but then again, you have to have voltage, the correct voltage, because if you put, for example, a 35Z5 tube that's used as a rectifier in most 5-tube radios uses 35 volts on the filament. If you put that in on a 6-volt power supply, you're not going to see any glow, obviously. And if you put 35 volts on a 6-volt tube, you're going to blow it out it's going to light up like a light bulb for a second, and that's going to be the end of it. So you do have to have the right filament voltage. An ohm meter will simply tell you if the filament has continuity.
Yeah.
That's as far as it goes. So let's look at the tube tester here. Ray, you want to bring the camera in a little bit?
Okay. Yeah, let's do it.
I have a tube here that the Instruments Company model TV11 tube checker that we use here at the museum in the shop. Again, it's an emission type tube checker, which is the middle of the road type of tube checker. The first thing you do with a tube checker when you want to check a tube, this is the tube we're going to check. It's a metal type tube, so you can't see if the filament's glowing or not. So obviously if you have this tube in your radio and you want to check it, you need a tube checker or an ohm meter to check the filament. You can't see the filament light up in this tube, obviously. So the first thing we're going to do is turn the tube checker on, let it heat up for a second. This checker has the capability to tell you not only if the electrons are boiling off the cathode and hitting the plate, but it also has the capability to tell you if the tube is shorted. So we're going to look at a couple of things here. The first thing we want to do is switch down to where it says line here, and we want to set the line voltage on this tube checker so that it's okay. So we got our line voltage set. Now we're going to go to regular, which is testing, and we're going to plug this tube. This is a 6SS7. We're going to put it in the 8-pin octal tube socket. You notice there's different tube sockets on this to fit different situations. It goes down to 4-pin tubes, which is the very early tubes used back in the 1920s, 5-pin, 6-pin, and it even does the 7-pin tubes that were used during World War II. The tube checker has a chart. This is a roll chart right here that you can find your tube number on it. What I've done, though, to keep from having to run the roll chart back and forth, I've copied the roll chart onto a computer file so that I'd have a reproducible chart in case this thing ever went bad. These things tend to strip out after time and they slip, and so you're trying to check a tube and it's slipping, and you have a problem. With this system here, I can reproduce this or reprint it anytime I need to. Alright, being a 6-volt tube, we're going to look at this. It says it wants us to put it on 6.3 volts for the filament. It wants us to put it on switch number 2 in the filament, the F position. You notice it says F, N, P, and K. The F is filament, N is a neutral setting that's used for neutralizing, P is for the plate voltage, and K is for the cathode. So everything stays down in the K position except the ones that they're telling you to put up. We're going to put the 6.3 volts on number 2 here, which is going to put it to the filament winding, or the filament pins on this particular tube. I'm looking at the 6SS7 here, which is what this tube is. All right, it also tells me that I need to have pin 4 in the plate position, and I need to have this loading control over here, which is what controls the plate voltage going to the tube, in position number 3. So it's on number 3, and I'm going to go ahead and I'm going to raise the plate switch number 4 into the plate position, and you notice that the meter's reading good. So that's telling us that this tube, even though it's an old tube, is still a good tube, and it's way into the good section, so it's not even weak. It's a good hot tube that we could use if we needed to. And that's basically how a tube checker works. Now, what you want to do before you take the tube out is turn everything off. Then you can go ahead and remove the tube. Have to remove it carefully so you don't break the socket. And let's set this aside because we know this is a good tube. I have a box of tubes that I was testing, and it's tubes that someone gave me. Some of them are bad and some of them are good, and we've been testing them and weeding out the bad tubes. So we know that tube's good. We can put it in our good tube box. The museum here has, Ray, if you could swing the camera around, this is kind of a makeshift situation here that we're trying to clean up and index our tubes. But this is 2 rows deep of spare tubes of everything going back to the very 1920 tubes and all the way up to the last tubes that were made in the 1960s. We can pretty much find a replacement in here, either with substitution or with the actual tube that we need for almost any tube that was used in radios, including transmitters, all the way up into the 1960s.
Does this have a zoom?
Yeah, the zoom is this little knob right here.
Oh. Okay, hopefully that's going to show.
Okay, good. So that's our tube supply here at the museum. If you're seriously into restoring radios, still running?
Yeah.
Okay. If you're seriously interested in restoring radios, it pays to look for not only tubes on the internet. You have to be very careful buying them off of eBay because some people are asking exorbitant prices for tubes. But it pays to have a supply of tubes if you can find them, particularly tubes for the newer radios. I mean, if you're doing like 5-tube AM radios that were made in the 40s and 50s. It pays you to have a 6SK7 and 6SA7 and some of the tubes that were used in those radios. And you can generally find those tubes kind of cheap on eBay if you're careful. We have a Philco 1929 radio that we restored here recently, and we needed to get a couple of tubes for it. And we found out that we were bidding on Type 26 tubes, and one set of Type 26 tubes was going for well over $100. It had already bid up that much. Looking around on eBay, we found another set of them for $30. So we went ahead and bought the $30 set and put it in our radio and got the radio playing. And some poor guy probably paid $130 for the same two tubes. So, you know, that's what you have to be careful of. But anyway, that's the basic tube theory for radios. We'll be back a little later with another series or another show on how to restore a typical 5-tube radio that was made after World War II. So take a look for that and be looking for us.
And thanks for watching.